Okay, hello everyone, and welcome to our fireside chat session today with Michael Munsey. Michael is VP at Siemens EDA. We'll be starting in just a moment. Okay, welcome Michael, and thank you everyone for joining our fireside chat today. The fireside chat's with Michael Munsey, VP at Siemens EDA. Thanks for joining us, Michael. Maybe you could just... Hi, how are you? Maybe you could start by telling us a little briefly about your current role at Siemens EDA.
Sure. Yeah. So I have a great role right now because I focus in on the strategy that ties together both the EDA side of things as well as the PLM side of things. So it's a lot of fun right now because the way the industry is going, and we'll talk about this more, is really when we look at the tools and the methodologies that we need to do, it's starting to really move from just talking about semiconductors to talking about entire systems and the way systems work in much larger systems. And we're seeing the need to share a lot more technology and methodology across from, traditional EDA tools as well as what was traditionally used in multi-physics simulations and looking at mechanical design. And it's all kind of coming together right now. So being able to look at the whole scope is really interesting, and be able to share experiences and successes from both sides to come up with a strategy and a solution. It's really exciting right now.
Oh, for sure. If you are watching us live today and you have a question for Michael as we're going through the chat here, we'll be asking some questions from the audience towards the end of this session. Please go ahead and ask your questions in the Q&A tab, which is on your right. Maybe I'll just start by asking Michael, what do you think is driving developments in chiplets and heterogeneous packaging overall?
Yeah, so there are a couple of things. We talk a lot about Moore's law and being able to continue along that path is really forcing us to look at different things, right? Because it's becoming more difficult to continue down monolithic silicon and be able to support that through the whole process. When we look at systems design, really we're looking at much more advanced systems and being able to leverage a lot of different technologies going forward. When we look at things like sustainability now, we need to really start figuring out how to make our devices much more sustainable, how to be able to manufacture them in more of a sustainable fashion. So it's kind of like a confluence of pushing the state of the art, but also being able to deliver these things in a manner that they're going to work and still be sustainable for the future moving forward.
Can you give us maybe some examples of how sustainability is driving these kinds of technologies? How is sustainability influencing design and production?
Absolutely. There's the aspect of sustainability around the design itself. There's the aspect of sustainability around the production of it. And then you look at things like sustainability of the entire products that ultimately semiconductors go into. If you look at NVIDIA's latest chips, right? We're talking about chips right now that are consuming over 1,000 watts. And there was an IBS report that just came out saying the latest design is probably going to be between 1,200 and 1,500 watts. So that in of itself, if you think about those types of chips in data centers multiplied by the thousands, things like that are ultimately going to become an issue because we're going to have to power them somehow. We're going to have to cool them. And we have to start getting a handle on that. One of the interesting things is if you look at, we're talking about here about chiplets design and advanced packaging, right? Even for a monolithic chip, if you look at the progress that's been made in advanced packaging, they mentioned that just things like backside power delivery is going to be able to reduce a couple hundred watts of power on these huge chips, right? So, but the whole industry really needs to start thinking about, instead of designing just to meet the requirements, designing to, exceed the requirements and do everything possible to reduce the amount of power in these chips, right? Because otherwise we're just going to be producing things that will be impossible to power. Another study, I think, it was to drive the future needs of AI and AI computing is going to require another 47 gigawatts of electricity in the grid in the United States alone, right? Which is 47 nuclear power reactors, and we're not building nuclear power reactors right now. So it's you definitely need to get a handle on all that, right? So there's the whole notion behind how do we actually produce chips themselves that are going to be more sustainable in terms of the resources that they're going to need moving forward. Now, the flip side is now how do you manage them and be able to produce them in a sustainable way? And a lot of efforts now have been starting to look at actually how we build a fab and what a fab looks like. In the past, typically you would build a fab just like you built the fab before. You make it bigger sometimes, you have more lines in it, but the idea was why change something that's already working? Well, now we're at a point where we really need to worry about what it takes on the sustainability side of things. And when we build those fabs, and people are now starting to look at what it's going to actually take to make that fab more sustainable. And that's really going to need ways to be able to simulate and be able to predict things early on in the design of the fab. And so when we talk about things like digital twins, the semiconductor industry has been producing digital twins of semiconductors since the 1960s. It's the only way, right, to do it because we're dealing with something that we never really see it built until it's done. So the only way to do it is entirely virtually up front. And we do that very, very well. So now we're starting to look at how do we build a digital twin of a fab and understand not only what we call the fab subfloor, which is things like the water chillers, the HVAC systems, the distribution, and how that's going to affect the entire fab, but ideally start looking at what it looks like also to produce the chips themselves, which means having discussions now about building digital twins of the fab equipment itself and actually have a fully functioning virtual model of that fab where you could simulate production and be able to optimize things moving forward.
Can chiplet technologies contribute to sustainability directly, maybe by consuming less power overall, or are they easier to fabricate?
Yeah, so absolutely, right? So the idea that smaller chips are easier to fabricate, right? So, you just get a notion of just by doing things at a smaller scale, you would be able to save, right? But the other way to look at it also is if you look at the entire chiplet itself, or the entire package with the chiplets in it, you could start questioning whether everything in there needs to be at the latest process node, right? And the answer to that in a lot of cases is no. And so you could also start reusing a lot of previous or older designs where performance isn't as critical and really start to mix and match different designs. This is perfect like for the automotive industry where you're using existing proven technology that doesn't need to be at the leading edge in terms of performance. And just by having these smaller chips put together, you're going to save power. You're going to save power on the interconnect also when you look at how you tie all these chips together. And ideally, you should be able to begin to produce much more sustainable devices at that point. It brings up now the question also of the supply chain and how you measure sustainability within the supply chain also when you choose different chips that you want to use. And that's a whole nother set of questions where, we're looking into providing solutions as well.
Got it. Did you want to mention the SEAGREEN initiative at this point?
Yeah, absolutely. So Siemens has had what's known as the SEAGREEN initiative, which really looks at the product carbon footprint when you actually go ahead and manufacture things. And most of the semiconductor providers all have initiatives to have, net zero carbon by 2030 or sometime around 2030. But that really requires measuring, how good you're able to do that and produce things. So the Sea Green Initiative, started off in some other industries to begin with, and now we're starting to look at bringing it into the semiconductor industry. It's already something that's been established in automotive and battery development and aerospace and chemicals and many other initiatives. And the idea here is that instead of taking a single number, which is an average of what your footprint looks like, it actually uses real data that's measured during the manufacturing process. And it's the idea of pulling in all of this manufacturing data and be able to actually understand where you are dynamically in terms of being able to reduce the carbon offset when you're actually manufacturing things. Because the interesting thing is when we looked at the electronics in the electronics industry, the PCF, the product carbon footprint, is actually driven more by the supply chain than it is by the end producer of the actual electronics products, which means the semiconductor is part of that supply chain, right? So that's one of the largest, pieces of introducing, the carbon footprint in the whole flow. There have been a couple of studies done, and the latest I've seen is somewhere between 0.3 and 0.5% of the entire carbon footprint for the planet right now is semiconductor production, right?
Wow.
That's a sizable number when you look at it. You could narrow it down that much, and that's definitely what we're starting to look at and actually provide that real-time data. And then that's also going to allow fabs also to, as they go towards net zero, make it a requirement of their suppliers to be able to say, this is what our footprint is. And you can actually see what the footprint is for the chemical suppliers, for the electricity suppliers, for the water and the water management and everything. And you can actually begin to see what that total number is going to be and be able to measure it and be able to reduce it moving forward.
Yeah. What can be measured can be improved, I guess.
Exactly. Yep.
Yeah.
That's exactly right.
Okay, sounds like if chiplets are going to contribute to sustainability, we better get started with chiplets as soon as we can.
Yep.
What do you see as the biggest technology challenges when we're bringing chiplets together or working with advanced packaging today?
So, it falls down to, the bandwidth, the interconnect, bringing this all together. But as I stated before at the beginning, it's also looking at the entire system now. That chiplet in that package now becomes an entire system, right? And so in the past, when we've talked in the semiconductors, when we talk about power, performance, and area, right? Now when you start packaging multiple chiplets, now you're worried about cost, weight, cooling, and it becomes a multi-dimensional problem that starts to become, larger in scale as you start to really try to optimize all these different factors. And these factors now are not just electrical or semiconductor, because you start now bringing in some mechanical and now analysis that needs to be done between the mechanical world and the electrical world at the same time to be able to produce these parts.
I mean, what do we need to kind of effectively produce 3D ICs today?
So I think the first thing is to have an intelligent cockpit. And, we just announced the innovative 3D product, right? And the idea here is you can't always be dependent on experts solving every single problem along the way, because you have to be able to make a lot of these trade-offs in real time. And this is the idea now. How do you bring in some intelligence from tool sets to help people make the right decisions at the right time and reduce a lot of the longer iterative type feedback that has to happen, right? The longer you wait to the closer to the end where you spot a problem, the longer it's going to take to fix. So you want to try to keep the iteration loops as small as possible. And so this is where, when we now start to go actually digging down, and when you look at the entire problem, that you realize there's pieces of which fall directly into the world of EDA and semiconductor design. There's pieces that fall into it more of the board level parts of design. But now you start getting into MCAD things when you start thinking about the packaging itself and all the pieces in the packaging and how they'll be assembled. And then you also, in the world now of multi-physics simulation, where you're looking at stress, vibration, thermal type issues. And so all these need to start to come together to be able to produce a full solution. And that's one of the unique advantages with the Siemens solution, because we have all those pieces put together. And it goes back to when we talk about digital twins and be able to model digital twins. Because if you look at the entire solution, you have tools like Aprisa that are handling the routing within the substrate, right? So using EDA chip design technology as part of the packaging. Then you look at bringing in some of the Expedition solutions with our Expedition package designer to be able to actually, assemble everything within the design. Then we bring in tools like NX, which is a MCAD tool. And, when I started in the industry, we never even worried about that, but now we need to worry about the pieces of the packaging that go together and be able to bring that in. You look at thermal modeling. So here's a case where we bring the Calibre tool set, but also bring in a piece of SimCenter, which is our multi-physics simulation, to be able to produce a new tool, Calibre 3D Thermal, which allows us to do the thermal analysis of the entire system within the package. And then we also have the full SimCenter products themselves also to be able to do vibration and structural and stress and warpage and those types of analysis. So that's the unique thing about Siemens, that we have the full breadth of technology, bring it into a single cockpit that now allows us to start to be able to integrate these tools, be able to do the iterative turns that need to happen. And again, not have to always go out to the expert in any area by having that now within the cockpit. And then you go talk to the experts when you need to solve specific challenging problems as you go along.
I think there are multiple platforms available now for developing 2.5D and 3D designs. How would you advise people on what to look for in this kind of platform?
Well, and so it goes back to the types of problems that you need to solve, right? And I say is that you could go and look at multiple platforms, but do you get everything you need, or do you have to start integrating with other tools that are out there, right? And Siemens is providing it all at once. Some of the other platforms require you to go out to potential partners where the tools may or may not be fully integrated together. Some of the other solutions out there have partners that actually have ecosystems that aren't easy to integrate into. So now you have the challenge of trying to partner with a company that doesn't necessarily want to fully integrate the tools themselves. And do you want to spend more time trying to assemble the solution and make all the integrations work, or be able to get all the technology you need right up front that are already integrated?
How do digital twins fit in when we're talking about 3D designs?
Yeah, so they fit in multiple ways, and it kind of shows you how connected everything is. So we do a very, very good job, as I mentioned already, creating a digital twin of the semiconductor device. So now the idea is how you start now creating the larger digital twins. And I mentioned that heterogeneous package itself is a system, and you need to be able to create a digital twin of that system as well. And now we're talking about a system that is EDA focused, MCAD focused, ECAD focused, right? So it goes across many domains, and you need to be able to model that within that multi-domain environment. And so that system itself needs to be capable of, handling the digital twin, and then feeding that also into the larger set of products. And later on, we could talk a little bit about the different products. But bringing up the idea of the digital twin, it's not just modeling it at that point. You also want to link together the digital twin of the design with the digital twin of doing the manufacturing, because that's going to allow us to do some levels of optimization that we haven't done in the past. If you look at the automotive industry, aerospace and defense, right, they not only create digital twins of the product, but they create digital twins of the manufacturing, and they bring the two together and do a lot of simulation. Case in point is that if you look at the automotive industry, 30 years ago, you were required when you brought out a new car to produce hundreds of prototypes, because you had to send them to the crash lab and just destroy them to understand, are you going to protect the passengers in there? A lot of automotive companies now do that entirely virtually, and they only produce 1 or 2 prototypes for the last crash testing that has to be done in real life. And that's because the nature of the models and the nature of the analysis is so accurate now that you could actually see in real life how the car is going to behave when it hits another car, if it hits a stationary object, and you can even peel back the layers of the car and look at the structural damage. And that's the idea of tying the 2 digital twins together. So now if we look at for semiconductor design and then actual packaging, the goal is now to be able to do something similar. So we have hyper accurate digital twins already now of the design. So now we need to start focusing in on those digital twins of the fabrication. As I mentioned before, you need to build a digital twin of the fab. Ultimately, you want to start bringing in the digital twin of the actual equipment in that fab. And then with the goal being to be able to simulate the manufacturing with the virtual model we have in a virtual universe, and start to be able to do process optimization, technology bring up all in a virtual manner. If you bring up a new process node, it takes months sometimes to get to the 95+% yield that you want to see in the fab. That's a lot of waste. And again, when we talk about sustainability, if you're throwing away a lot of wafers and using a lot of chemicals, not good from a sustainable point of view. But if you could create that model and now be able to drive it and do all the optimizations up front, you start to be able to hit yield a lot faster and be more sustainable that way. Then you could actually, once you're in the factory producing products, by the fact we have technology that allows you to measure what's happening during manufacturing, you could start taking that information and now trying to feed that back into the design aspect, and now produce better libraries, better methodologies based on real-time manufacturing data. And what we're creating now is this loop of going from the virtual world, bringing up products and finding issues in the virtual world first, addressing those and fixing them all before we ever start manufacturing. So we now optimize the manufacturing process. And then in the real world, start collecting real data that we could use to analyze where we're at, analyze how to improve things in the future, and feed that back to produce better libraries, better tools as we move forward.
I'm intrigued by the idea of linking the digital twins for the chip or the chiplet design and the fab. How complicated a process is it to link these 2 very different digital twins? And can you tell us anything about what's involved there?
Yeah, so this is all really new, and this is it's not going to be easy because it's going to rely on many different parts and people working together. But we've already started partnering with different companies. We just recently signed an MOU with Intel to help Intel in their new fab designs to start looking at what that digital twin of the factory is going to be moving forward. And that's the first step. So we could start actually modeling the factory and modeling the infrastructure that's associated with the factory. That's going to be step 1. The next thing is to start working with the semiconductor equipment providers. The good news is a lot of them already use technology that would enable digital twins. And the fact that if we could start working with them and getting the actual digital twins of that equipment moving forward, then we can start building a larger model. So this is not something that's going to happen overnight. It's not something, that you could wake up tomorrow morning and say it's going to be there, but it's something that we really need to start driving towards moving forward.
Speaking of going forward, how do we think the kind of landscape of 3D IC development and production is going to change over the next few years, maybe next 5 years or so? What do you think is going to happen?
Yeah, so it's probably going to change very quickly, and it's going to be driven by the types of designs. What I really see is that more and more designs that were monolithic are going to be, actually 3D ICs moving forward. Again, it's a cost function for the customer. It's ultimately going to be a performance function, a sustainability function as we talked about. And I believe that what we're going to see is much more time spent in making designs that can be chiplets and can be reused. The goal is to ultimately have people providing chiplets, and much like the world of PCB design, we could go to different vendors and get different chiplets. That's the goal of where we want to drive towards. But I think we're going to see, at least within companies themselves, doing more designs which are chiplet enabled, that will allow, at least within a single customer, being able to produce these designs moving forward. And then from that, start looking at what it's really going to mean in terms of taking best in class designs to be able to produce these multi-company systems within a single package.
Yeah, I think we're seeing that trend too at EE Times, of semiconductor companies kind of becoming chiplet providers or becoming more vertically integrated, basically making their own chiplet designs and selling those. How do you think that kind of trend is going to impact everything?
Yeah, so and it's I think it's just going to follow the way that we've seen systems companies become vertically integrated already, right?
Yeah.
And so you're going to be going from vertically integrated at the PCB level down to vertically integrated at the 3D IC package level, and then you're going to really start to see different factors driving the system design itself, right? And we're looking at going from what I used to call a software-enabled flow to now a software-defined flow and a silicon-enabled flow, where these systems are going to be actually built around enabling larger product features moving forward in many different industries.
Yeah, makes perfect sense. Okay, I think we're starting to see software-defined products are going to emerge as well. Another big trend, right? Changing the landscape quite a bit. How do you see the emergence of software-defined products? How is this going to influence the whole semiconductor and packaging industry?
I usually tell people, think about your cell phone, right? You use it every day, but you never think about the hardware that's inside that cell phone, right? Some of the most technology advanced hardware is inside that cell phone. If you look from the processor capability to the radio to the infrastructure that drives everything. But what you use on a daily basis is the software that sits on that phone, right? And the software defines the user experience, right? And that was kind of, the realization that, you're going to have software-defined products. Well, that's a cell phone. At another end of the scale, let's look at the car that you drive right now, right? The car itself, you hear the term software-defined vehicle, right? And really, the software is driving the user experience of what you do day to day inside of your car. And to the point that one of my colleagues, just bought a brand new car. And, in the past where, let's walk around, let's look at what the car looks like from the outside. Let's open up the hood and let's look at the engine, right? The first thing he did was take me inside the car and start showing me everything he could do with inside the car, right? And everything he was doing was software driven, right? The whole user experience about sitting inside that car is all software driven. And you think about it, you spend more time inside your car than you do outside looking at your car. So it's natural that the user experience is going to be driven from behind the wheel, sitting inside of the car, right? But that's a case of, again, another software-defined vehicle. And I had another one of my colleagues, we had this discussion a long time ago, and he's like, look, unless you're designing a steam locomotive, the product you're designing is probably going to have software driving on some type of infrastructure inside of it, right? And now what we're seeing is the entire design process is starting to get upended because of the software-defined product.
Yeah. Okay, let's talk about some real-world applications. Go for it.
So a couple of them, right? So let's look at two of them, and then we can kind of like dive down into how that's changed the entire product design flow. So a partner of ours, Sony, just designed a AR VR headset to use with our NX MCAD product. And the idea here is that you actually now interact with the mechanical design process by wearing this headset. And you can actually reach out, touch the part, move it around, stretch it, take things apart, right? And it's used to enable better design. So when they first designed this, they had specs of what they wanted to do, but everything that was being done in software. And it required making sure that the underlying platform itself would be capable of running the software workload. And what quickly became a realization is that in a lot of these product designs, the idea of having off-the-shelf processing technology that you could put in your design has kind of gone by the wayside. And what you really now are worried about are producing compute platforms that can handle the software workload, because there is, in fact, so much software that needs to run on these devices. If you go back a couple of years, the old Verizon commercial where the guy walks around, "Can you hear me now?" Or when you're on your computer and you get the little spinning wheel, right?
Yeah.
Those are all applications of having a processor platform that's being hung up by the amount of software workload that needs to be run at the time. It's an inconvenience when you're on your phone and you drop a call or you can't hear somebody. It's an inconvenience when you're waiting for something to happen on your computer. But if you're in a car and the processing platform locks up because of the software workload, you're going to kill somebody. If you're in a plane, you're going to kill people. So, it's critical to have the right processing platform. And this has enabled a whole, new industry. It started off, first with ARM, and ARM offering IP, and then ARM licensing the instruction set. And now you look at RISC-V licensing an instruction set that allow people to build the compute platforms as part of their entire design process. And it's all about now that custom platform that's going to handle that software workload, because the software itself is defining the user experience. And there will always be trade-offs. There will be things that you need to do in software versus hardware, and there's things you're going to have to move from software into hardware just because of performance reasons. But you need to be able to handle all of this up front, right? This trade-off up front to narrow down the optimal platform before you start to move forward. So you need to worry about, getting that right. So you got to get the requirements right. You have to separate the software and the hardware requirements right, and then follow down this path. And that path itself is different, because you have software leading hardware now, as opposed to when I used to do chip design, which is I get my design to a point where then software could be able to be brought up on it. It's now the other way around, that the software design's happening first, and then you need to now be able to run that software and verify that software on different platforms, which is why, we have different levels of emulation and different levels of compute power to be able to start doing software and hardware verification at the same time. And just the notion of that software design is ultimately going to affect the product design. It's going back to that Sony AR VR headset, that because of the software that needed to be run on it, it affected the actual processor package that was being run on. That processor package had to be moved around in the product design itself to get to a point where it could be cooled effectively, because the last thing you want is a 200-degree part right next to your temple on your head, starting to burn you. And then that itself impacted the PCB design, and the PCB design then impacted the overall product design, right? So you had software requirements actually impacting the entire product design moving forward, which is totally different from the way things were done even 10 years ago, where somebody designed the product, you put all the compute platform on a PCB, and then you brought the software up on it. we're now seeing software requirements actually drive the overall product design.
And do you think all types of electronic products will move towards software-defined, towards software-defined concepts? Yeah, you spoke about cars earlier, but it's going to be everything, right?
Yeah, it's going to be everything, and as in most cases, to various degrees, right? But the idea that once you have a product up and running, it's more than likely going to be software updatable. For example, you could buy an electric car today, and 5 years from now actually have a better car because of the software updates. But you have to be able to predict, and support that workload and those updates moving forward. And most product designs, again, going back to sustainability, you don't really want to be tossing away a gadget every 18 months to 2 years if you could continue to produce a better product by driving more software in it, right? And so that's ultimately going to be the goal. And it also works both ways, that sometimes there are certain products that have to be of a certain form or function. If you look at any of the earbuds that you could use right now, one of our customers in their product has a PCB with 47 different bends in it, right? When you think about that, to be able to get that to fit into the product. And now here's a case where the overall product design, right, is now dictating the infrastructure that the electrical systems would be in it. You have to worry about all these different bends and everything, which now actually dictates the package that you could use for the electronic components that go in there, right? So now going back to the whole idea of packaging design, you have product design dictating the form and function, which is going to dictate the packaging design. But now again, those earbuds are also software upgradable. And so you have to realize that, you'll probably be adding features and functions to that. So you have to make sure what you're designing up front is going to be capable of the extensions that you need moving forward.
Coming back to sustainability there, I think one thing I'm picking up on is that it is going to have to be an industry-wide effort. This is from the fab, the design, to the products, to the software, to everything that goes into making electronic products is going to need to be more sustainable. This is something everybody should be thinking about, right?
Yeah, absolutely. And everybody should be doing it. But you also need the tools and the infrastructure to support being able to do it and be able to do it in an efficient manner. The way I used to think about it is that you think that you feel real good about yourself when you're given a target to hit, right? And you meet that target, right? Sometimes you feel real better if you not only meet the target, but you exceed the target, right? But we're all very busy, right? And if it's anything we could do to enable the exceeding of those targets, it's ultimately going to lead to, more sustainable devices. So it's not just going to be people driving this. You're going to need the tools to also make it easy to drive this. And then you're going to need to be able to feed into an entire system that's going to make it easy to be able to achieve a sustainable world. I was just in China last week. And one of the things that caught me is that 4 out of every 5 cars I saw on the road were electric. And it's easy to get an electric car in China because they have the infrastructure to charge a car all over the place, right? So there's a case of, you make it easy to be able to adopt electrical vehicles when it's very easy to charge them anywhere you go, right? Yeah. So it's all about, driving towards this is really about, having the tools and the methodologies that make it easy to be able to do moving forward.
So we're going to move to our Q&A session in just a moment. If you have a question for Michael Munzey on sustainability, chiplets, digital twins, anything you like, please pop it in the Q&A tab, which is on the right-hand side. Michael, I wanted to ask you, I was going to ask, what advice would you give to engineers or people kind of entering the field of chiplet design or packaging design? I guess number one would be think about sustainability, right?
Yeah, absolutely. Think about sustainability and think about everything that you do with that in the back of your mind, right? So when you're talking about, when you're talking about like power performance area, right? The idea of producing something as low power as possible, that drives towards sustainable goals, right? Um, if you're even at the product design level, what can you do to make that product more sustainable, make it last longer, right? The idea of having the notion of design for sustainability, right? We've talked about in the past design for manufacturing, design for yield. What we're really talking about here is design for sustainability, right? Ultimately moving forward and being able to, having that be as much of a goal as everything else that you do from a point of product design. And the software defined product is a long way of going, making devices more sustainable. That if you could make it software upgradable, so something you buy today is as good, if not better, 5 years down the road. That requires you not to have to keep buying new platforms to get the technology and the features and the functions that you need out of something moving forward.
Yeah, that makes perfect sense. Okay, how should semiconductor and IP companies prepare for the future? What would you advise companies to do to prepare for the future to stay competitive once chiplets start becoming really mainstream?
Yeah, so I think the goal here is to make your designs, first of all, make your designs desirable in the marketplace. And so again, that's not only having the fastest device out there, having the most compute power by having the least amount of power, realizing that the companies that you are going to be providing your designs to or your IP to are in this world where we're looking towards net zero carbon offset. So your designs will be more desirable to those companies to adopt and use if it helps them reach their goals moving forward, right? And this is the idea that these types of sustainability goals, feed into the entire supply chain and become, a competitive advantage. So if you have the ability to produce something that's more desirable because it's more sustainable, then that's a way to feed into the overall supply chain moving forward.
So we have a couple of questions here from the audience, which I'm going to read out. First one here. The loop from manufacturing to design through libraries and design kits. The audience member is saying this exists today already in PDKs. What's the new value from digital twins?
Right. So that loop has always existed because the people doing the manufacturing are the ones that produce the design kits. But that is a point in time, right? You bring up a new process, you produce the PDK, and then you deliver the PDK to your customers moving forward, right? What we're talking about here now is understanding now as the customers start producing designs with those PDKs and they go into manufacturing, start to learn from what happens during the manufacturing process. What does the ramp to yield look like? What parts of the design are causing problems with the ramp to yield? Can we improve that in new designs to accelerate ramp to yield later on? Look at what does it take inside the manufacturing plant. How many times is it going through multiple steps of the lithography? How much time does each step of the lithography take? Because the longer it is at a given step inside of lithography, the more electricity that you're using, right? Can you improve that later on? And the idea of using that information to make the process better moving on forward. So it's the nature of this dynamicism in the feedback loop to be actually improve things moving forward, right? So instead of it being more of, here's the PDK to do your design, and you do your design and you're done with it, have a continuous feedback loop that's continuously improving the process as we move forward.
Thank you very much. Okay, next question from the audience. I'm going to read this out. At the Chiplet Summit 2023, Siemens presented on the thermomechanical behavior of chiplets. In light of that, what's the current state of chiplet technology regarding the ability to withstand multi-physics phenomena, particularly in relation to local power hotspots, and how to address these?
Yeah, and so this is actually what really has led to the Innovator 3D platform. So, when we looked at that, what we were looking at is a bunch of different analysis done by a bunch of different tools. And we didn't have them all in a single cockpit. We had the tools available, and we had the ability now to actually, do these types of thermomechanical analyses. What we've done now within the cockpit is we've taken pieces of the technology that are important. So, for example, when I mentioned Calibre 3D Thermal, right? This is the idea of taking Flowtherm, which is a multi-physics tool that's usually used independently, take pieces of that technology into Calibre also, and now to start be able to do some of these 3D thermal when we start looking at hotspots in chip, especially as we start stacking chips and how the hotspots affect the entire stack in the packaging. So this is the idea of now starting to integrate a lot of these technologies. And again, by doing the integration, it allows you to quickly do this analysis without having to do separate tools, getting some of the the expertise out of the loop and let them worry on about the more difficult problems, and being able to do quick analysis, try different placements, try different simulations all within this environment, and be able to optimize things. Something I didn't mention also, I should bring into this also, is part of the technology that we have available is a technology called HEEDS, which is part of our SimCenter on the multi-physics side of things. And what HEEDS allows you to do is really look at multi-objective optimization across multiple tools. So when we start doing a lot of the what-if analysis and different placements and different stacking and different interconnect with different simulations, we're going to begin to start to be able to optimize some of this and allow you to do multiple iterations automatically and be able to zero in on the right solutions moving forward.
Thank you very much. Here's our next question from the audience. Is sustainability really achievable given consumerism for new products, whether it's appliances, auto design, aesthetics, including energy use needs, especially for a product whose life is only 5 to 10 years, like a cell phone or a TV?
Yep. So I think the way to look at it is that sustainability has to happen, right? It's becoming a requirement, right? So yes, given that people still have this desire to have the latest, greatest gadget. Even myself, I was one of those people that every time a new phone came out, I had to get a new one. Now I find myself keeping my phone longer because I've figured out how to upgrade it and use the tools effectively, and I don't need to do it anymore, right? So if the entire ecosystem produces products that continue to deliver and suit basically against the requirements of the consumers, then you would drive them towards not necessarily always having to buy the latest, greatest thing because it's meeting the needs. And then this goes back to the idea of being software upgradable, which leads us back to talk about software-defined products. And it's because we need to do it, right? It's not a nice to have. We have to do something about sustainability.
Yeah, agreed. Okay, next question from the audience. This is about digital twins. The fundamental issue with a very exact and detailed digital twin is it has the potential to expose trade secrets, or at least to enable reverse engineering by competitors, especially with AI, they're saying. What do you feel about this for digital twins?
So we've always had this issue, right? If you look at if somebody's GDS2 Oasis got leaked, right? That fundamentally is the ultimate digital twin of the semiconductor that's being defined, right? So the issue now is how protecting those digital twins, right? The digital twins themselves are owned by the customers. They need to protect them the exact same way that they need to protect their own IP in ways of doing things today, right? The question now is, in terms of when we start building digital twins, it's creating the ecosystem now that is safe and secure to be able to do the levels of modeling without exposing, trade secrets and things like that. And as with anything, what happens is that if you get an advantage by being able to bring things up in the virtual world, then that's going to drive the industry to move more towards producing digital twins that could be used in a manner to do those types of optimizations, right? So, the issue here isn't so much as if you do it, you're going to expose it. You need to do it in a way that's safe and secure and protected, just like you do with your own IP today, and make sure it's safe and secure, and the environments that these digital twins run in are safe and secure.
Yeah, thank you. Okay, another question from the audience. Do you feel it's feasible to have a dynamic blueprint for digital manufacturing in a fab? How would you sync continuously and sustainably between the virtual twin and the physical production environment at the pace required?
Yeah, so the one thing that's unique about this industry is the rate and pace of change, right? And the idea here is that once you produce that first digital twin, people will always say, well, how accurate is it anymore? Well, the first step is to get to the point of producing that first digital twin and then being able to have the ability to update that moving forward. So again, as I mentioned before, the largest hurdle is going to be to get to the point to really have that digital twin. Once you have it, then it's going to be a goal of being able to, update it incrementally as things change and move over time. We do it already on the semiconductor side of things. We're constantly producing new designs, up until the point that we tape out, right? It's an incredibly dynamic environment with thousands of people involved. It's capable. We're able to do that. And, let's focus on that first step of getting to the point where we actually have it, and then be able to figure out how to do the updates quickly and easily.
Thank you very much. We have another question from the same person. This is related to what we were talking about earlier, I think. How would you protect a comprehensive digital twin from an IP perspective? I understand discrete modeling's easy to secure. Surely integrations complicate this as we talk more about systems engineering.
Yep. So it's much in the same way that we protect our IP already today, right? So there's ways to encrypt things. There are ways to do the development under certain aspects of it. Even with IP, when we talk about IP protection, and we're looking towards using things like blockchain, right, to be able to protect IP and also make sure it hasn't been changed or tampered with in any single way. So it's the customers themselves have to make sure they have the right protections in that IP that they manage themselves. But then there's ways to look at also how do we protect the sharing of that IP when we look at how we're going to take a digital twin from somebody else to incorporate in the model. And we can look at technologies like blockchain there, ultimately the same way we're doing it for design IP, to make sure that that is trusted and secure. And we could have a whole nother hour conversation on, trusted and secure supply chains as well, and the way that we could actually start protecting those models as we share them amongst ourselves.
Thank you. Last call for any more questions from the audience. If you have a question, or if you're typing it, please finish. Okay, in that case, I'll just ask Michael, do you have any final thoughts you wanted to share with us on sustainability, chiplets, or anything else?
Yeah, no, definitely. I think, all of this is all tied together, right? And, it's almost like we have a need for sustainability. We have a need for chiplet design. It's all connected, right? Both are driving each other. And you asked the perfect question is, as a new designer, or as you get into doing this, what can you do in terms of, enabling sustainability, enabling designs to be used in a chiplet economy? And it's keep in mind that all of this is all going to be connected moving forward. And it's going to be a real exciting time over the next couple of years as all of this develops.
Very exciting. Michael Munsey, Siemens EDA, thank you so very much. Thank you for the interesting talk, and thanks to everyone in the audience who asked a question. Thank you everyone for watching. The next session will start very shortly.
Thank you for watching. To learn more about this topic, check out the links in the description. And if you enjoyed what you saw, Like the video and subscribe to the channel.